Here, Newton's law of universal gravitation.
Mm,
As a review, according to Newton, every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. So this force acts along the line joining the two particles. So in formula, F sub g is equal to g m1 m2 over r squared. So everything with masses are having gravitational attraction. And take note, force of gravity is only attraction, no repulsion.
mm,
Okay, and G here is different from small g. Capital G here is 6.67 times 10 to the power negative 11 Newton meter squared per coulomb squared. No, not coulomb squared because it's for electrical force. It's kilogram squared, evident from the formula M1 and M2 here. So in other words, the force of gravity is dependent on the two masses of the interacting bodies and the square, inversely proportional to the square of the separation distance between them. So the effect of the distance is much because it is to be squared and it's an inverse proportionality. Okay, so it's somehow like a third law, like here, moon and earth. Gravitational force exerted on earth by the moon. At the same time, there is a gravitational force exerted on moon by the earth. And a common conceptual question is, how do you compare their forces? Of course, they're equal because by third law, they have equal and opposite interaction. Okay, so there they're equal and you can compute based on this formula. Okay, so solving g, a small g, which is acceleration due to gravity from capital G, it's possible if you equate the force of gravity by for example, an object m on Earth. For example, you are the m there on Earth, and you experience acceleration due to gravity. So your weight is mg. And at the same time, you can also equate it to the force of gravity, which is the g, capital G, m. M is your mass, and then mass of the Earth, so because you're on Earth, and then r squared, which is basically the radius of the Earth, because from the center of the Earth to the surface of the Earth could be radius, except if you climb up to Mount Everest, for example. So here we can solve this g, acceleration of gravity of the Earth's surface by having this. Yeah, you can cancel out in this case, you can cancel out the small m because it's present on both sides. So what is left is the gme over r squared. And take note that the g can be computed based on location and elevation. So here in the table from Giancoli, physics by Giancoli, we have here New York, G is 9.803, San Francisco, 9.800, and the elevation, take note, is 0 here. But if you go to Denver, 1,650 meters above sea level, it's 9.796. And I think Talaytay Argao is only 180 meters above sea level. So that is not so much a difference. 4,300, 9.789. Okay, so take note of those. Okay. So yeah, in other words, if you have masses, so naagi acceleration jet, no, naagi gravitational force with each other. Okay. And if you want to, as a review last time, if you want to compute the g, the acceleration due to gravity at the top of Mount Everest. So we all know Mount Everest is 8,850 meters above sea level. So what is the acceleration due to gravity of objects allowed to fall freely at this altitude? So you compute g. So from the derived equation, you compute g. So you use this gravitational constant, 6.67 times 10 to the power negative 11 Newton meter squared per coulomb squared, and then the mass of the Earth given. And then here you are going to add the radius of the Earth plus the height of Mount Everest, 8.9 kilometer, and you convert that to meters. Okay, so there, you convert that to meters so that you can cancel out units, meter squared here, and you square this one. And you can cancel out the kilogram squared, in this case, uh, makancel. We have 1 kilogram here, a Newton. Okay, take note there is a Newton here. And Newton is also kilogram. Okay, Newton is kilogram meter per second squared. So in this case, it will become kilogram squared and it can be also cancelled with this. So what is left is meter per second squared. Okay? So that is a reduction of 3 parts in 1,000 or 0.3% in Mount Everest. So that is not too much.
Mm.
Okay, so that's a review of what we had last time. And satellites and weightlessness. So we review weightlessness last time, like in an elevator, say, or weightless, and we related to satellites that you can feel weightless. So this is an example of a satellite, International Space Station circling the Earth. So take note in this figure, artificial satellites launch at different speeds. Escape velocity from Earth is about 40,000 kilometer per hour. So meaning when you say escape velocity, that's the time that you are no longer gravitationally attracted to the Earth, and you can escape from the Earth's gravitational attraction and move to space. And if you maintain a circular orbit, which is around 27,000 kilometer per hour speed, so you can have the circular orbit. If 30,000 kilometer per hour, an elliptical orbit, and you are kept inside the gravitational attraction with the Earth so that you can circle around the Earth if you are in a satellite. So a moving satellite falls out of a straight line path toward the Earth. So instead of having a straight line path by inertia, that the object will continue in a straight line unless acted by unbalanced force. So mauni siya because of its inertia. But since there is a unbalanced force, which is the gravity of the Earth, it tends to circle or move in an elliptical orbit. So that's it. And if you exceed this 40,000 kilometer per hour, you can escape from the gravitational pull of the Earth. Okay, so that's for the satellites. So an example, if you also, because we are talking about satellites, and since there is a gravitational pull towards the Earth, we have what we call a centripetal force, which
Mm.
is towards the center, provided by the gravitational pull. So the gravitational force can be equated to the centripetal force, MA, di ba? Wherein the centripetal acceleration is V squared over R. So in this case, you can solve for the V here, and you can cancel out the mass. One of the mass here is the mass of the satellite, the mass of the Earth. And then what is left is G times ME. And then the R can be here, can be uh, cross multiplied here, but then there's another R here. So one R left because it will be canceled. So that's why it's GMER and then V squared so that you can extract the V squared and make it V so you get the square root. So that's why we now have square root of GME over R. Okay. So an example here is we have a geosynchronous satellite. A geosynchronous satellite is one that stays above the same point on the Earth, which is possible only if it is above point on the equator. So why? Because in the equator, it's the oblate spheroid siya. So in the equator, it will have this uh, it's possible to have that geosynchronous satellite that stays above the same point on the Earth, okay, to have the same point lang. So because the center of a satellite orbit is always the center of the Earth, so it's not possible to have a satellite orbiting above a fixed point on the Earth at any latitude rather than 0 degrees, which is at the equator. Okay, ang center of the orbit is always at the center of the Earth. Okay, so that's the main reason. So geosynchronous satellites are commonly used for TV and radio transmission, for weather forecasting, and as a communication relays. So example here, determine the height above the Earth's surface, such as a satellite must orbit, and B, such as satellite speed, and compared to the speed of satellite orbiting 200 kilometers above Earth's surface. Okay, so approach to this problem. To remain above the same point on Earth as the Earth rotates, the satellite must have a period of 24 hours. So period of 24 hours comparable to one whole complete rotation of the Earth. So we can apply Newton's second law, F is equal to ma, wherein the acceleration is centripetal, which is v squared over r. If we assume the orbit is circular, there we have discussed uniform circular motion, and we have this centripetal acceleration. Okay, so we have that, and we proceed. Okay, so for the solution, the only force on the satellite is the gravitational force, and you equate it to the centripetal force. Okay, as what I have said. So here, this is the gravitational force and the centripetal force of the satellite here. Due to the Earth, but yeah, acted on the satellite. So that's why we have the mass of the satellite here, mv squared over r. So we don't know v, but as we all know, v can be computed by having this period, satellite revolving around the Earth in one period, which is 24 hours, and you convert that to seconds, 86,400 seconds. So one whole complete period around the Earth is one whole circumference, 2 pi r. And we all know 2 pi can be done in the calculator. R is the radius of the Earth. You can review that, which is uh, given, nanay radius ng Earth to. Okay. But in this case, we substitute this into the satellite equation above and obtain after canceling MSAT on both sides. So here, M of the satellite can be cancelled because it appears on both sides. And if you solve for R, so you substitute here the V with 2 pi R over T. So it will be squared man. So 2 pi R ang T should also be squared. So 2 pi R squared and squared. And it will become, okay, rearranging the equation, it will become R squared here and R. Okay, so it will, you arrange the equation, it will give you r cube. So after canceling an r, we can solve for r cube. So makancel ang isa ka r in this case. Okay. So if you have that, we have GME T squared over 4 pi squared because 4 many 2 squared is 4 pi squared. So 4 pi squared. And the R cube will be here. It will become R4, di ba? Ma-R4 na siya. Divided by R. Okay, you divide it so that it will become R cube. Okay, so here r cube na. And if you solve it, you'll have this r cube and take the cube root. You take the cube root of this whole thing, okay, whole equation. So this is now the r. 4.22 times the power of 7 meters or 42,200 kilometer from the Earth's center. We subtract the Earth's radius, which is 6,380 kilometer, to find that a geosynchronous satellite must orbit about 36,000 kilometer, about 6 times the radius above the Earth's surface. So aron geosynchronous siya, so dapat its orbit is about 6 times the radius of the Earth. Okay, so that's just a derivation of the equation. And it is shown that it's better to derive the equation first rather than plug in values. So have the algebra first before you plug in values. And then the second is we solve for the V. Okay, from the previous equation, we can solve for the V, GME over R. So here you can have 3,070 meter per second. Okay, and about 11,000 kilometer per hour, we get the same result if you use 2 by r over t. Yeah, pwede sad kini mo gamito na equation, okay, or this equation. You will have the same result. And the equation in part B for V shows that V is inversely proportional to the square root of, is proportional to the square root of 1 over r. So for RE plus height, we get this one. Okay, iarang relate in that case because our previous question will is asking, okay, for a while, it's asking for this, the third equation, the third question. Okay, the third question. Compare the speed of a satellite orbiting 200 kilometers above the Earth's surface. So ipa-compare lang. So to do it, this one, you just have the proportionality because all others are constant. So this kini lang ang mo affect, the r and the velocity here. So the velocity nga nakuha here is 3,070, r is 42,200, and r is 6,580 kilometer from the 200 kilometer man daw above. So you just add the radius. So you compare, so r over r prime, okay, and then 7,770 meter per second. So about 28,000 kilometer per hour. Okay, so that's it. Just algebra actively applied in physics. Okay, so let's move on to Kepler's laws. So for Kepler's laws, we have three laws also. The path of each planet is about the planetary motion. It's also in relation to the gravitation and also uniform circular motion and having an elliptical orbit. So for this Kepler's first law, the path of each planet around the sun is an ellipse with the sun at one focus. So this is an ellipse here. Okay, an ellipse, you don't have ellipse no in math. So if you don't have the ellipse yet, so in a circle na kay one center. In an ellipse na duha ka focus, so two foci. Okay, we're in, excuse me, in one of the foci, the sun is there. Okay, so kung naa diri ang planet, mauning naa siya sa, uh, how do you call that? Perihelion. Okay, it's near,
Perihelion.
yeah. Kung far siya, aphelion, di ba? Okay. So that's the elliptical orbit. And second law, each planet moves so that an imaginary line drawn from the sun, the planet, sweeps out equal areas in equal periods of time. So this one, if nasa sa perihelion, dapat mo sweep daw in equal areas in equal time. So it is doing so, the planet is doing so by moving greater speed here. Okay? And slower here aron ma-equal siya. Anyway, we have only something like a concept for this. So the two shaded regions have equal areas. The planet moves from point 1 to point 2 here. At the same time, it takes to move from point 3 to point 4. Okay? Planets move fastest when closest to the sun. So that's why I said fastest siya there is a perihelion. Okay, so that's it. And yeah, so this one, sweeping equal areas and equal periods of time. And the third law, there's a formula to be applied. The ratio of the squares of the periods t of any two planets revolving around the sun, so ratio of planet 1 and planet 2 nga periods nga square is equal to the ratio of cubes of their mean distances from the sun. So take note, planet 1 also, S1 sa diri, then S2. Ang S here stands for the mean distances from the sun. Okay, so the mean distance equals the semi-major axis, or half the distance from the planet's near point N and far point M from the sun. So here, distance mean equals the semi-major axis. Near point o far point, di ba? Na near point from the sun, yan po yung far point, iyang gi-half. Okay, so that's the mean distance. Okay, so there. And Thus, if T1 and T2 represents the periods, the time needed for one revolution about the sun for any two planets, and S1 and S2 represent their mean distances from the sun. So this is the formula now. And you can rewrite this one by applying the squared. So we can have around ang 1 on one side. So S1 cube over T1 squared, imong i-transpose or cross multiply. And S2 cube, no, not S2. Yeah, S2 cube also. Yeah, because it will be cube. So S2 cube over T2 squared. Okay, here. Or this. Okay? So direct proportional sa isa ka planet, T1, directly proportional siya sa cube root. Ang iyang square sa period, directly proportional sa cube root sa iyang mean distance. Okay, kay gatungod naman siya. Okay. So these are the illustrations. Okay. And planetary data, if you have noticed, if ikuan ang S cube over T, you have noticed that they have constant ratio. So that's by third law. Di ba mao tong third law? Okay, here. The ratio of the squares of the periods T of any two planets revolving around the sun is equal to the ratio of the cubes of their mean distances from the sun. So there, if kaon mong ratio sa S cube over T squared of that planet, so more or less par-pareha. Okay? So, sample problem of this. Where is Mars? So, Mars period is 1 year. It's 1 year. Was noted by Kepler to be about 687 days, which is 687 days divided by 365 days for Earth is 1.88 Earth years. So, determine the mean distance from Mars, of Mars from the Sun using the Earth as a reference. So, ang mean distance daw. Kung know na nimo ang Earth. So, we're given the ratio of the periods of Mars and Earth. So, pwede nimo i-ratio ang Mars and Earth. We can find the distance from Mars to the Sun using Kepler's third law, given the Earth distance is 1.50 times 10 power negative 11 meters. So table 5.2. So this one, ini distance and the period. So S of Mars to Sun, S of Earth to Sun is equal to T of period of Mars and period of Earth. And then 2/3. Kay bawar man mo ano na 2/3 nino.
Mm.
Okay, kay 1/3 man to ni dire. Sakto? Okay, then i-remove nimo i-cube root both sides. So ang cube root is 1/3, so times squared, so 2/3 siya. Okay, so ang ratio S of Mars over S of Earth, we can have now base the period. 1.88 year ang sa Mars, and then sa Earth is 1 year, kay 365 days maraman sa Earth. And then in your calculator kay para pod mo ani. Okay, squared and then you get the cube root, or katong exponent, then 2/3 ang exponent, and that's 1.52. So Mars is 1.52 times the Earth's distance from the sun, or 2.28 times 10^11. So that is a sample problem. Another, Kepler's third law derives sun's mass and perturbations. So you actually can derive the sun's mass based on Kepler's law, or universal gravitation as well. So it's we derive Kepler's third law here, universal gravitation. So summation of all forces equal to ma. So this is the gravitational force acted by the sun on any object or planet. And this is the centripetal force, yeah, because this could be the centripetal force that makes the planet revolve around the sun. And we all know velocity is the circumference over the period. We can substitute it here. So from that, okay, imo ni ipuli din ha, okay. So in that case, may mo ning 4 pi because it's squared. So it will be 4 pi squared R1 over T squared sub 1, okay, M1. And then we rearrange this so we can cancel M1 because it appears on yeah, opposite side, same side. Yeah, you can divide it and then you'll get to 1. So T 1 squared over R1 cube. So it will become cube if you've noticed here. It will become cube here. And then 4 pi squared. So yeah, you will have this equation. So after having that equation, okay. We derive this for planet 1 is Mars, so you will have now the ratio of the period squared over the mean distance or the orbit radius. Okay, 4 pi squared over GMS. So in that case, kinitanan nga naa sa right side, okay, this one are all constant, di ba? Constant na siya. So if constant na siya, for everything is equal to another planet also, ngay na. Okay, t squared. So, for the second planet, so we can have, since the right sides of the two previous equations are equal. So, kini nga mga equation equal ni sa tanang planet man, equal ang mass of sun. And then, constant ang g, constant ang 4 pi squared. So, you can do that with the rest of the planets. So, that's why we can have this. Okay? And how to determine the sun's mass using that equation? So, using this equation, you derive ms lang. If you derive ms, so you have 4 pi squared r cube, ini, the r cube here, and g, and then t squared. Ang masamok-samok lang sa inyo kaning mga subscript, but ayaw mo ka threatened sa subscript. It's just there. And then you can have that and you substitute values and then the constant and then the period and you'll have that. Okay, to determine the mass of the sun. Take note, mass of the sun is huge, 2.0 times 10 to the power of 30 kilogram, di ba? Very huge ang mass of the sun. Yeah, ang earth, pila ra tong earth? Pila ra to yung mass sa earth if you remember? Maka-remember pa mo? Okay, so mass of the earth here given? Wala. Okay, so yeah, 5.98 times 10 to the power of 24 kilogram ang mass of the earth. Okay, ang mass of the sun is here, 2.0 times 10 to the power of 30 kilograms. Okay, and that's it for the discussion. And I will not give any assignment for the Kepler's laws, but only to read the modules. Okay, so question now, and you can turn on your camera if you wish. Any question?